Hopefully this is the last lesson I will miss for further maths for, well, the year. Let's see how we go. Today we'll be performing a regression analysis. So in the last lesson you'll recall that what we did, you can see it still on the calculator here, is that we produced the regression line for this scatter plot here. And the benefit of having this rather than a line of best fit is that all of us will get exactly the same line for exactly the same point. So we get the exact same equation. Today what we'll do is work out how to actually draw this line ourselves. Okay, so given a scatter plot, how do I actually put that line on there, along with performing what we call a full regression analysis. So without further ado, let's get stuck into it. So when we draw the actual line of least squares on a scatter plot, we don't just copy it off the calculator. So you don't sort of look at the calculator and go, oh, I think that point there is roughly, and I think that point there is roughly. We need to get it exact. And this is the method that we use. So here's the points here that you're going to use to sketch it. But rather than read through them, what I'm going to do is actually go ahead and do it and show you how it's done. So let's see how it works. Right, the scatter plot below shows the rainfall in millimeters and the percentage of clear days for each month of 2008. So we've got the EV here, the RV here. So the equation of least squares regression line for this data set is this. Okay. Now, what we'll note is that the line of best fit is going to look something like this. So if I was to draw it by sight, I could imagine it might be something like that going through the points. But that's not exact, okay? And we need to use this equation here to actually plot the line. All right, so here's how it works. Draw this line on the scatter plot. So the first thing we're going to note is that given the equation, we can use the equation to generate 2 points. All right, so I'm going to go and let's do Control N for a new doc. And I'm going to add a calculator. All right, so I can see very quickly that it's going to be 131 take away 2.68 multiplied by. And what we're going to do is put in 2 particular percentage of clear day points. Okay, now the first one we should use, if possible, is the furthest point possible, which is 0. And we hope that that will give us a value. And I can see here, for those of you who know how to read these equations, you'll see that that's the y-intercept straight away. So it's going to be 131. So this is 122, 24, 26, 28, 30, 32. So 131 would be here, okay, at this point here. I'll just show you, though, what we'll do is we'll actually get the calculator to spit out that answer by putting in percentage of clear days is 0, and I want to know what the rainfall is. So if I type 0 in now, it'll tell us that the answer is 131. Then what we're going to do is put the furthest most point on our graph. Okay, so the furthest point. So I go back, like so, hit enter, and remove the 0, and type in 30. And it says 50.6. So here is 50, here's 52. So I'm going to go halfway between and a little bit lower. So pretty close to 50 itself. It's hard to get it exact. All right, and once I've done that, what I'm going to do is get my ruler. So it's really important that you have a ruler in your SAC and exam, and you simply join up those points. Like so. And there's your line of best fit or regression line. Okay, so that's the one that all of you will get roughly. And what VCAR do then is they kind of, when they assess this, they know it's not going to be exactly the same because it's hard to plot the point 50, 0.6, etc. And so they just make sure that the line will go through particular values there and particular values over here at the bottom end. Okay, so important to note that there is a limited amount of flexibility. All right. Now, use the equation of least squares regression line to predict the rainfall for a month with 35% of clear days. Write your answer in millimeters correct to 1 decimal place. Okay, so that means that we're going to go to our calculator and go 35. Okay, so 35 is going to be somewhere like down here. All right, so it's almost going to be about 40, I can see. All right, let's type or go to the calculator and type it in. So I go enter to copy that down, change that to a 35 and hit enter again. And I've got 37.2 millimeters. Now the unit's not required because it says write your answer in millimeters. So that is 37.2 is in millimeters. But I'm going to do it anyway, no harm. All right, the coefficient of determination. Okay, so the coefficient of determination is r squared. And it's that value there. Interpret the coefficient of determination in terms of the variables rainfall and percentage of clear days. So here's the point where you get the script out. Okay, and what we're going to do is note that this as a percentage, 0.8081, we multiply that by 100, is 80.81 as a percentage, 80.81%. So what we say here is 80.81% of variation in. All right, and what we do here is we always put the RV in this spot, okay, in rainfall can be explained by variation in, what is it, percentage of clear days. So this is the EV here. All right, and the final question is determine the value of Pearson's product moment correlation coefficient. So this is Pearson's value, or they're asking us for the R value. So remember, we've been given the R squared value. So what we're going to do is square root the R squared value to get the R value. So 0.8081. And that gives us the answer 3 decimal places, 0.898899 to 3 decimal places. But the really important thing is then you go back to the graph and you have a look at the way the scatter plot looks. And you'll note that this scatter plot goes top left to bottom right, okay, which means that the R value is going to be negative. So it's very important that when you square root this number here, that you actually go and match it up with the graph over here and check whether it's negative or positive. Invariably they make it negative because that's really what this question is testing. Okay, one, it tests whether you know that it's the square root, but the other one tests whether the student will match it up with the graph. All right, so let's go for it and do a full regression analysis. Okay, so this is similar to what you might get, say, in a SAC. All right, so what we'll do first of all is follow this basic process, and it steps you through step 1, step 2, step 3. So the first thing we do is construct a scatter plot to investigate the nature of the relationship between the two variables. Okay, so here we've got the relationship between age of a car and price of the car. Okay, so we can see here a 1-year-old car, 32,500. A 1-year-old car, 30,500, etc., etc. So we can see here that as the age of the car increases, the price of the car decreases, which seems to make sense. The older the car, the cheaper it is, at a base level anyway. All right, so let's pop this data into our calculator. So we're going to go Control N for a new one, so get rid of all of this stuff here, and we'll go a lists and spreadsheet. Here we'll put the age, and here we'll put the price. All right, so I'm going to pause the video while I type this in. Okay, so I've just typed in the data, and just for review purposes, let's go and hit Control Doc, and what we want is data and statistics. Tab around, so you got tab, and then I'm going to hit age is the EV, tab and down, and price is the RV. And it looks pretty similar to what I've got up there on the screen. So there's our scatter plot. Now, at this point, you'd be sort of going, yep, that definitely looks linear. There's definitely no real outliers or nothing that looks totally unusual. So we're going to proceed with the regression analysis. So from calculating the correlation coefficient to give a measure of the strength of the relationship, so from the scatter plot, we can see that there is a negative linear relationship, so we know that, between the price of the car and its age. The correlation coefficient correct to 3 decimal places is, so we're going to find out the R value. Now, to get the R value, we'll go Control and left click to go back to this screen here. And what I'm going to do is place my cursor on C1 and go Menu, 4, 1, and I want linear regression in A plus BX form. So that one. So the way I want it is the EV, this is really important that we get them around the right way, so is age, the RV is price, scroll down, and it wants to pop the results in D. That's fine, I would have preferred it in C, but it doesn't really matter. Alright, so we hit OK, and we note that in column D then the results of the regression analysis go in there. So I can see here that my R value is negative 0.64, which suggests a strong negative relationship. Alright, so the next thing we'll do is determine the equation of the regression line, and what we've got is the car is the response variable and age is the explanatory variable. So we are going to fit a least squares regression line, so using the t-inspire, write the equation with values correct to the nearest dollar and hence add the line to the scatter plot above. So what we need to do is write the equation. So remember that what we're going to do is use the context to write it. So we start with the RV, which is price. So we're going to say that price equals, alright, so then we write it in y equals a plus bx form. So a is this value here, and they want it to the nearest dollar. So that's 35134. Alright, then our b, this is our gradient, is this value here. So we're going to say take away 3935 multiplied by, and it's the x value, the x is the EV, that is the age. So here is our equation of the regression line. So price is equal to this a value here, or the y-intercept, subtract the gradient multiplied by the age. Right, so you just use the same approach each time. Now remember, there's another way to do this. What you can do, let's go Control and forwards, and you go Menu, Analyze, Regression, and Show Linear, and that will also give you the equation of the line. And it will give it to you in kind of, I think, a little bit of an easier way to write down rather than in pieces. It gives you the whole thing. So it really is up to you how you want to get the equation. Alrighty, so then what they want us to add that line. Okay, so yeah, at this point what we'll do is we'll go Control, Doc, and add a calculator to that. And then we'll plot a point at either end of this scatter plot to draw our regression line. Okay, so our equation is this one here, so 35134 take away 3935 multiplied by the age. Now remember what I suggested earlier is that what you do is you use a number on either end of the scatter plot. So in this case it'll be 0 and 8. Now there's going to be a little problem with 0. So if I put in 0 and hit enter, it's 35134. Now what's this? This is 31, 32, 33. It's off the grid. So what we do is we just choose a point closer in. So I'm going to go with 1 and see what it tells us for 1 and see if I can plot that point. So go up, enter, type in 1, 311. So that's 31,200. So I can do that one. So here's 31,000. 31,500, 32,000, so it's around about here. So I'm going to plot the point there. All right, at the other end, 8 is probably going to work for us, so we'll hit, come on calculator, that and type in 8, 3,654, so 1,000, 2,000, 3,000, 3,600, so a bit over halfway, and we're going to plot that point. All right, so then what we're going to do is basically you get your ruler, and you what you want to do is make sure that your line goes through those 2 points and extends all the way to the end of the possible grid squares. Okay, you can even go further than that if you want. All right, so I'm going to try and do that. Whoops, probably use a straight line tool. Yep. I'm just going to go through like so. All right, so there is our equation of the regression line, and it is being plotted. All right, so what we do is we then need to interpret the coefficients of the least squares regression line. Okay, so for the equation, the slope or gradient b predicts the change in y when x changes by 1 unit. I'll explain what that means in a sec. So that's how we interpret b. And if it's positive, then it increases as x increases. If it's negative, then it decreases as x increases. And then this other thing, the y-intercept predicts the value of y when x is equal to 0. And that's what a is. All right. So let's use the equation. So this is it formally written. This is the same thing as what we wrote down earlier. So it's good to see we got that right. So let's interpret it. So on average, price of a car, that is the response variable. So this is like a script, so you'll use this a fair bit. All right, on average, price of a car, the response variable, will. All right, so we have a look at the gradient, okay, and we look at the sign of the gradient. So this means that it's negative. Will decrease, so we're going to use the words decrease if it's negative and increase if it's positive, by 3,935. So we actually say the number in context, okay? Decrease by $3,935 for this is going to be an increase in age of 1 year. So this part here is usually the 1 unit, and this part here will be decreased by the value of the gradient, okay? So that's how we basically interpret it, and we use basically the same approach for every single equation that we get. Okay, so you can use this script to help you write your answers. And let's interpret the y-intercept. On average, the price of a car that is 0 years in age is $35,134. Can you explain what the y-intercept means in context? So a car that's 0 years in age means this is the price, this is the predicted price of a new car. Okay, because if I said to you, I got a car that's 0 years old, then you'd go, ah, yeah, so you got a new car. All right, so we can use the regression line to make predictions. So what's the price of a car that is 5.5 years old? So we could look at the graph and go, here's 5, here's 6, so this is 5.5. So I know the answer is going to be roughly 14 or 13,000, but we actually need to use the equation and the calculator to work it out. So that's going to be price is equal to 35134 take away 3935 multiplied by the age, which is in this case 5.5. So we've already got this stuff in the calculator from when we plotted the lines, so we're just simply going to use that and change that to 5.5. So the price is equal to $13,491.50. What's the price of a car that is 240 years old? So a very old car. So we're going to use the equation for that because it's certainly not on the graph. and it says that it is, so I'm not going to do all of the working out for this one, I'm just going to write it down, negative, what's that number, $909,266. All right, so that's what you're going to pay for a car that is 240 years old. Negative nine. Basically, this is suggesting that they'll give you $909,266 if you buy a car that is 240 years old. Now, that doesn't make sense, and we'll talk about that in a sec. So the price of a car that is 10 years old. So this seems to make a bit more sense. So let's do that one. All right, and it says that a 10-year-old car, where's my mouse gone? There it is. Okay, is negative $4,216. All right, so you might have heard the words extrapolation and interpolation from General Maths last year. Basically, it's assessment of the reliability of prediction using the least squares regression line, because that's the whole point of getting this line here, is to use it to make predictions. All right, so if I call up the car dealer now and I go, hey, listen, I've got this car, it's 7 years old, Toyota Corolla, what do you think I will get for it? Then what he or she would do is pop that into their regression line and go, I reckon you'll get blah, blah, blah. Okay. Now, the reliability of the prediction, though, is contingent on whether it's being interpolated or extrapolated. All right, so what is interpolation? So the position of the value is within the range of the data set. Extrapolation, okay, the position of the value is outside the range of the data set. Now, interpolation, if I've progressed with linear regression, is reliable. Okay, that means that I've got evidence to suggest that this is true. Now, extrapolation is either less reliable or unreliable, depending on certain factors. All right, so let's just see what these three predictions were. So 5.5 was the first prediction. So here is 5.5 here, and we can see here that the largest value that I've collected data on is an 8-year-old car. The smallest value I've collected data on is a 1-year-old car. 5.5 sits within those numbers there. So 5.5 is indeed what we call interpolation. There's evidence to suggest that the pattern fits for that number. All right, let's have a look at the next prediction I made. So it was 240. So remember, 240 is all the way along the line here, all right, which is clearly outside or above the number 8, which means that it is less reliable, or in this case, totally unreliable. And the final one was 10 years. Now, 10 years was close to 8. Okay, 8 was the largest number, but still, this is outside the range of data that we've collected. The oldest car that this car yard has sold is 8 years old. All right, so we really don't know whether that's a reliable prediction or not. And in fact, looking at the number, okay, it suggests it's not reliable, because it seems to suggest that at 10 years old, they're going to give you, like if I go into a car yard and buy a 10-year-old car, they will give me $4,216 for buying it, which doesn't make sense. All right, so extrapolation is a less reliable process than interpolation because you're going beyond your original data. So which of the predictions made before? So 5.5 would be interpolation. 240 was I can spell. And 10, even though it was close to the highest number, which was 8, it was still outside the range of the highest value. So we're going to say that this would be also extrapolation. Extrapolation. Okay. All right, the next thing we'll do is using the coefficient of determination to give a measure of the predictive power. So we know that the R value is this value here. Okay, we looked that up before and wrote it down. Okay, where was it? There it was there. So what we'll do now is get the r squared value. Okay, so there's a few ways you can do that. So you can actually just square this value here, but we can actually go get it from here. So here's the r squared value. So we're going to write that down. It is 0.929794 ... Okay, and what we'll do is write the report using this number. Let's do it correct to 2 decimal places. Okay, so we're assuming assumption 2 dp on the percentage. All right, so what we're going to do is say that 92.98% to 2 decimal places, so we write that as a percentage of variation in, now remember what we do is we put the RV in first. Okay, so what we're going to say is the in variation in the sale price of cars can be explained by variation in age of car. So the explanatory variable. All right, and it has a lot to do with it. Okay, so you can see here that the age of the car is can explain a lot about the price you get. Okay, notwithstanding the fact that if I roll up with a 1-year-old car that's got basically dings all over it, is in really bad shape, then the variation can be explained by the condition of the car. But generally speaking, it's got to do with the age. All right, so the next thing we're going to do is check what we call the residual plot. All right, so how do we do a residual plot? So we're going to go Control and forward to the Scatterplot, and there's an option, I vaguely remember, residuals. So what we're going to do is go to this plot, this thing here. So we go Analyze, Residuals, and what we'll do is we'll say Show Residual Plot. All right, and what we can see underneath here is the residual plot of this. All right, so just a quick review. A residual is the vertical distance of a point from the curve. That is the difference in the y values. So we can see here that we've got the straight line, that's the regression line, and we've got the points here. And the residual is how far away a point is from the line. Okay, now remember the line is the predicted value, the point is the actual value. Now when a point is above the line, that's going to have what we call a positive residual. Okay, so the residual is positive. When a point is below the line, it's going to be negative. Okay, so that means it's got a negative residual. All right, now when we go to the scatter plot, okay, we can when we have a look at it, okay, we can see here that there's a pretty random scatter of points both above and bottom and below the line. And when that happens, we can assume that the plot is the original plot, or the points here were linearly related. Okay, if a pattern comes up here, like a parabola looking thing or something that has a distinct pattern to it, then it suggests that the original points were actually not linearly related. Okay, so when you see kind of a bit of random scatter here, that's actually excellent on the residual if you indeed have fitted a linear regression line. All right, so let's do some stuff with it. So from the scatter plot, we can see the residual value for a 6-year-old car. So here's 6. All right, here's the point here. So we can see that that's roughly 12,000. And we can see the point here is roughly 7,000. Let's go with those values there. So the difference between the two, okay, 12,000 and 7,000, we can see is roughly 5,000. And because it's below, we say that it's negative. Okay, so what does that mean? That is the actual price of the car is approximately $5,000 less than we would predict. All right, when the actual price of a 6-year-old car is $6,500. 500. Right, so let's calculate a residual. So calculate the residual error of prediction when its price is predicted using this here. Alright, so if we continue to calculate residuals, we'll find that some are positive or above and some are below, which is negative. And what we want to see is no clear pattern. Okay, that is, we want to see this random scatter around a zero regression line. So this is this plot here. Okay, so because the points are randomly scattered around the mean line, there is no clear pattern. There's a reasonable linear relationship between the age of the second-hand car and price we paid. So we can conclude the random scatter of points above and below the mean line on the residual plot suggests a linear relationship. So something like that. All right, and then you can summarize all of these things in a report. Okay, so these are all of these things. Now remember, we talked very quickly about nonlinear relationships. So if this was the original scatter plot and then the residual plot, what you can see is that the dots form more of a pattern. So this suggests that actually a straight line graph is not the best predictor or the best equation for this data. Okay, so yeah, so notes on how to create a residual plot. Let's go through that again. So I'm going to just pull that up. So you're going to go to Analyze, which is 4. So it's menu, 4, 7 for residuals, and then you're going to say, what was it again? Menu, Analyze, residuals, and show residual plots. That's 2. All right, I think we'll leave it there for the moment because the video is probably long enough for today, and we'll do a little bit more work on residuals in the next lesson.